Okay, so I'm going to talk about a case study. I went through that much faster than I thought I would. So, case study of a project I worked on at Foothill De Anza College. So here's a rendering of the building. It's a classroom building. Generally, on the lower parts down here, the classroom buildings facing south and facing north on the other side. So the concept for this building was to utilize automated louvers at the perimeter, and with a relief path into the atrium, and then relief out of the top of the atrium, so you're combining wind-driven effects with stack effects. And the project also utilized radiant slabs, so we had both heating and cooling embedded in the slab. So the question that I was tasked with answering was, how big should the louvers be on this project? Because they're going to use up wall area. It's going to eat up, they're opaque, right? So you're eating up daylit, or area you could use to put windows and daylight the space better, and also affects the look of the exterior of the building. So they wanted to, in some sense, minimize the amount of louver that they used on the building while still achieving good performance. So here's just the building's built so you can actually get an idea of what it looks like. Here's our NVTs, or natural ventilation terminals, above the window, and here's our relief path into the atrium, and then we have our relief path out of the atrium on top, and we have a weather station on the building that allows us to adapt to real-time conditions and control those louvers in real time. So the first step in my analysis, and I think in any natural ventilation analysis, would be to do a site study or analyze the predominant conditions at the site. So you want to analyze the occupied hours of your building. You don't care about, if it's a classroom building, you don't care what the wind is doing at midnight, right? So you want to isolate the data and filter the data that you care about. And what I found, the average temperature to be 9.8 miles per hour, and 95% of the hours that airspeed was above 4.5 miles an hour. And if the wind rose shows a very predominant direction from northwest there. So, okay, so because we have a backup radiant cooling and heating system, I was primarily concerned with the average conditions. So you might also consider using something lower. We could use a standard deviation lower than average to sort of represent the worst case scenario, even though zero wind would be the worst case scenario. But in this case, I used the average, and so I built my geometry in an external volume and oriented it such that I'm getting that northwest direction, and imposed the 10-mile-an-hour boundary condition on the inlet and a zero pressure on the outlet, and slip symmetry elsewhere.